It's a great pleasure to talk with you about the giant planets. I'm going to be focusing particularly on Jupiter and Saturn, with a bit about Uranus and Neptune. And on the left, you see the big list of spacecraft that have explored the outer solar system. Pioneers 10 and 11 went past Jupiter and Saturn. Voyager, Jupiter, Saturn, Uranus, and Neptune, the only spacecraft to go past Uranus and Neptune. Galileo went into orbit around Jupiter, had 34 orbits. Cassini went into orbit around Saturn, had 294 orbits. Took a lot of observations. The New Horizons flew past Jupiter on its way to Pluto. And then the Juno mission has been in orbit for 78 orbits and hopefully will survive another couple of years. There are two spacecraft on their way to Jupiter. One is Europa Clipper, the other JUICE. And I believe your next talk is going to be on the Europa Clipper mission. So I will not focus much on the moons. I'll focus on the planets today. So if we think about Jupiter and Saturn, they're both about 100 times the size of the Earth, or 100 to 300 times the mass of the Earth. Whereas Uranus and Neptune are much smaller, about 4 times the size of the Earth, 20 times the mass of the Earth. Now, I show you here the astronomer's periodic table because the constituents of these giant planets is very different from the Earth. And you have to realize that hydrogen is the dominant gas of our universe, with helium next. And then oxygen is the third. And of course, if you combine hydrogen and oxygen, you get water. So water is actually H2O, a very common molecule in our solar system, and plays a key role in many things, including life. So when we think about the gas giants, you can see that Uranus, Jupiter and Saturn are really mostly hydrogen and helium, whereas Uranus and Neptune have a lot of what we call WAM, water, ammonia, and methane, which combines hydrogen with the next most abundant atoms, oxygen, nitrogen, and carbon. But it has a layer of hydrogen on the outer layers. Now, when you think about the formation of the solar system, you can think of a young sun starting to cool down, having a big disk of material orbiting around this young sun. So it's hot close to the sun, and then it cools off further away. And at some point, the ice, what kind of water that's there, will freeze out to make this frost line, and you will begin to pull together pieces of frost or ice beyond there. Inside that region, you have rocks and metals condensing to make the terrestrial planets. Now, there's not a lot as they're low abundance, these rocks and metals. So you have small planets, Mercury, Venus, Earth, and Mars. But beyond the frost line, ices and rocks and metals come together to make the cores of the giant planets, and they're on the order of 15 to 20 Earth masses. And once you have that mass, it pulls in the hydrogen to make these gas giant planets. The very abundant hydrogen to make the gas giants. So when we look at the overall picture of these gas planets, these distances shown in units of astronomical units, or distance between the Earth and the Sun. You can see they're out beyond 5 times that distance, and going out to 30, a long way out, Neptune. The mass, 318 Earth masses to make up Jupiter. It is a big planet. 95 to make Saturn, and then much less for Uranus and Neptune. Now, it's more important to think about the density. We'll come to this next. And the composition, as I've already mentioned, hydrogen and helium plus WAM for the Uranus and Neptune. The last column here is the number of moons, and you can see a lot of moons for Jupiter and Saturn. Most of them are really pretty small. Similarly for Uranus and Neptune, they're pretty small. Now, when we compare Jupiter and Saturn, there's a factor of 3 difference in the mass, and since density is mass divided by volume, then Jupiter is going to be greater mass, and so it'll be much more dense than Saturn. In fact, when you look at the density of Jupiter, Saturn, Uranus, Neptune, and you put it in units of grams per cc, then 1 is the density of water. And so, in fact, Saturn would float if you could get a big enough bucket for it to sit in. So, Jupiter is denser because it's more mass. Has more mass. Uranus and Neptune are denser because it has less hydrogen, more water, ammonia, and methane. Now let's think about what pulls these planets together. So, as with all atmospheres, including the Earth, what's important is to think about the pressure associated with more mass, the gas in the atmosphere weighing down. And so the deeper down in the atmosphere, there's more pressure, you've got more stuff above, pushing it down and compressing it. So the way to think of this is to think of a planet's atmosphere being like a pile of pillows. And as you add more pillows, you add more pressure pushing it down. And so what happens is that if you add more pillows, it just compresses it. And then you get not a big difference in size. As you add more, the lower ones get squished and you have about the same distance. So if you look at adding more mass to a planet, this plot on the top right, if you add more mass to a gas giant, it grows bigger, but not a whole lot, just a little bit bigger. And so this is important when we think about gas giants around other stars, exoplanets. They do tend to be around the size of Jupiter, even if they're more massive or less massive, because of this compressibility. So let's look at what's inside these big gas bags. You've got here on the right the density. So going down through the planet, it starts very low density in the outer atmosphere, reaches about a density of 1, density of water, some way down, about 80% down. And then as you get down to the deep inside, it can be denser than rock and metal right near the core. Now, the idea is that if you compare with the size of the Earth, you would end up with this core of rock and metals, something like 15 Earth masses of that. And down deep inside, it also gets hotter as you go from the top down to the bottom. And that temperature says 20,000 degrees Kelvin. The units are not particularly important. You just need to know that that's about 4 times the temperature of the surface of the sun. So it's hot down there. And the pressure are really high. So 1 bar is the atmospheric pressure here on the Earth that you're breathing in around in the room. And it's about 100 million, 50 to 100 million times that pressure deep down in the center of Jupiter. That's a lot of pressure. So what does that pressure mean? Well, pressure is force per unit area. And so when you stand on your feet, you put pressure on the floor because of gravity pulling down on your mass. And then if you lift up 1 foot, half the area, you have a lot more pressure on that 1 foot. So if you think about the pressure of 1 bar, 1 atmospheric pressure, it actually is equivalent to having 5 people on your shoulders and the pressure through your feet. Now, it may not feel that way because you feel the pressure that you're breathing in the atmosphere doesn't seem very high, but indeed that is the pressure that we experience. Now, when we go to the center of Jupiter, it's not 5 people, but it's 1,000 elephants standing on top of each other, with the bottom elephant standing on 1 leg on a stiletto heel. So the pressure at the center of Jupiter is huge, right? That's the point I'm trying to make here. And at those pressures, hydrogen behaves a little different. So let's think about what it's like inside. We want to find out, is there a core of rock and metal? And then layers. The picture on the left is the sort of textbook view of a planet with distinct separate layers, or is it that it's more mixed up with the heavy elements dissolving in the outer layers? So that's what we sent the Juno mission to try and understand. So the way that works is we send a spacecraft that goes around Jupiter, and it sends radio signals back to the Earth. It transmits a signal, and the frequency of that signal back to Earth varies with the perturbation in the speed of the spacecraft because of the gravity inside Jupiter. So I'm going to let that run again because I want to keep explaining it. Oops, sorry. There we go. It's not wanting to run. The point is that the spacecraft speed varies as the spacecraft goes over lumps of mass inside Jupiter, and by measuring the change in speed of the spacecraft using the frequency of the signal sent back to Earth, the radio signal sent back to Earth, sending information about pictures and images and so on, but with looking at the frequency, you can measure the distribution of mass inside Jupiter that is perturbing the motion of the spacecraft. And that's very important to understand Jupiter's gravity. And what we're finding with the Juno mission is that there isn't a distinct core of heavy elements. It looks like the heavy elements are sort of mixed in with the layers of hydrogen above, and indeed some of the helium seems to be raining out, but the boundaries are fuzzy. It's not quite as distinct, sharp layers that you see in the standard textbook. The other thing is to think about the fact that deep down at these very, very high pressures, hydrogen changes its behavior. It begins to act like a metal. The electrons can move freely. So think about hydrogen. Molecular hydrogen has 2 protons and 2 electrons that are moving around each other, bound together in a molecule. And that acts like a gas, like a fluid. This is at lower pressures. You go to very high pressures, the electrons and the protons separate out and can move freely. So positive protons and negative electrons can move. And so you can have a current, electrical current going through this system. It becomes electrically conducting fluid at these high pressures. And we call that metallic hydrogen because it is electrically conducting. So when we go inside the different planets, we have different regions that are conducting. For the Earth and for Mercury, we have liquid iron deep down where magnetic fields are generated deep inside the Earth, deep inside Mercury. For Jupiter and Saturn, we have this metallic hydrogen layer, which for Jupiter is really large volume of the planet. And for Saturn is a smaller region. And so then, as you would expect, Jupiter has a much stronger magnetic field compared with Saturn. And then when we go out to Uranus and Neptune, the pressure isn't high enough to make liquid metallic hydrogen, but there is liquid water, and that has materials dissolved in it. And so it acts like our ocean, Earth's ocean, and is electrically conducting. So when you look at the table along the bottom of all the planetary magnetic fields, what you see is the top row is the size of the planet relative to the Earth. So here's Jupiter and Saturn, 11 and 9.5 times the size of the Earth. And then the size of the core relative to the size of the planet. And you can see for Jupiter, it's 90% of the planet is this conducting material, metallic hydrogen. Whereas for Saturn, it's only 60%. And so then if you look at the bottom, the strength of the magnetic field compared with that of the Earth, you can see Jupiter's is really strong, 20,000 times stronger than that of the Earth. And so big range in the strength of the magnetic fields across our solar system, depending on what's inside these planets and how they're behaving. Now, when you look at the nature, the sort of geometry of these magnetic fields, for Earth, we have our dipole magnetic axis is tilted about 11 degrees from the spin axis. Saturn, they're very tightly aligned. Jupiter, it's also about 10 degrees, a very strong dipolar magnetic field. But when you go to Uranus and Neptune, Uranus, of course, is tilted as a planet on its side with its spin axis pretty much in the plane of the planets. And the magnetic field is tilted, highly tilted away from that. Similarly at Neptune, highly tilted and irregular. And if you actually map out the magnetic fields of Uranus and Neptune, they are very non-dipolar. The Earth, Jupiter, and Saturn at the top, they are very dipole with the magnetic field coming out of the pole in the North Pole in the case of Jupiter and Saturn, or going into the North Pole for the current period of Earth. And then for Uranus and Neptune, it's very weak and irregular magnetic field produced in that sort of ocean of a weakly conducting water layer. Now, when we think of the effect of rotation on these gas giants, because they're fluids, if they're rotating fast, in particular if they're low density like Saturn, you end up with a fatter equator and a smaller polar radius. So you fling material because of this rapid rotation out towards the equator. So they're flattened by about 10% in the case of Saturn. Now let's think about the atmosphere and what we're seeing, and then what's deep down in the atmosphere below. So we look at Jupiter here, which is, we've got 11 times the radius and 318 times the mass. And if we look at the sort of a map of the atmosphere, you see these belts and zones, alternate stripes of yellow, orange, and white. And if we look at a movie of this made by the Cassini spacecraft on its way to Saturn, it shows you the belts, the white ones going to the right, the orange ones going to the left, great red spot in the middle there. And then you see, I seem to have stopped, but if you look at the Earth one above, we also have belts and zones, fewer belts and zones, just a few, not lots. And the continents get in the way. We've got oceans. It's more complicated. Rotation isn't as strong for the Earth. We only spin every 24 hours, like 10 hours for Jupiter. But you can see we still have this sort of rough belts and zones system on the Earth. Now, what we have to think about with Jupiter is the chemistry of the atmosphere and the clouds that are produced. What are these clouds we see in that movie? Well, the atmospheric pressure at the cloud deck is actually pretty similar to the Earth. It's about 1 atmospheric pressure. And we have ammonia ice, ammonia clouds above, and then we have water clouds much deeper down. And then we have a mixture of ammonia and sulfur, ammonium hydrosulfide, we believe, in the intermediate layer. And so you have multiple layers of clouds where material cools off and condenses. So when we look at these clouds, we're seeing fresh clouds of ammonia ice coming up, and then we're seeing orangey clouds, which we assumed it was made out of sulfury stuff that makes it orange. But we'll come back to this. What causes the color on Jupiter? Remember, the atmosphere is 99% hydrogen and helium, so it's not causing the color. There's something else that's causing the color to be returned to. So here we are, we have these cloud layers, and when we look in visible light, we just see the outermost layer. When we look in infrared, and the movie on the right is taken by the Juno GRAM instrument in infrared, you see heat coming out between the cloud layers from deep down inside. That makes it glow in the infrared, and the colder upper layers are dark in the infrared between. Now, what we want to do is to look deeper below the ammonia cloud down to the water clouds. And to do that, we have to use microwaves, longer wavelengths than infrared, to look deeper down into the atmosphere. And so we can do that with the Juno mission. It tries to understand the atmospheric circulation by combining the observations of the clouds on the top, the microwaves of the infrared deeper down. And you can see these are quite strong winds that you see with the eastward and westward jets. So let's think about how this microwave on Juno works. It's a spinning spacecraft, but it scans the atmosphere underneath and looks at the amount of heat coming from deep below, because as the planet was formed, it got hot inside, and that heat slowly escapes. And you look for the amount of absorption of that heat at different wavelengths by the cloud layers, the water cloud layer, the ammonia hydrosulfate cloud layer, and the ammonia cloud layer on top. So we combine visible observations and infrared for the top layers. We look at the microwave channels for the lower layers, and then we use gravity measurements and magnetic field measurements to probe the deeper layers of Jupiter. So what do we find? Well, the first hints of deep circulation were found when we looked in the microwave data that suggested some circulation of material. So let me illustrate that a little better. This is the concentration of ammonia, and these are going through multiple orbits, one after the other. Now, PJ means perijove, so each time the orbit comes close, we call that a perijove, and they're numbering here 5, 6, and so on. And we've now got many more, but you can see there's a variability in the circulation here of the ammonia. It's not quite as simple as these static layers that the textbook were showing. So what we're seeing here is a deep circulation with strong winds going left and right, stuff going up, stuff going down. And to illustrate this, here is a movie that gives you a sense. You've got east and west winds, you've got a turnover of material. This is a combination of the effects of rotation, Jupiter spinning every 10 hours, a bunch of turbulence, heat coming in that turns over, and then east and west winds, wind shears driving turbulence. And so these combinations of rotation, turbulence, and convection produces this system of turning over the atmosphere and driving these east-west winds, as well as generating the spots, vortices. Now, Juno got the first view of the poles. We hadn't flown over the poles of Jupiter before. And on the left, we have visible images of the atmosphere. And you can see, as we said, we have this sort of white and orangey color, which is the main clouds. The bluish color comes from the same physics that causes our sky to be blue. I'm looking out of the sky here in Boulder. It's this beautiful blue sky. And this is because of Rayleigh scattering, or scattering of blue light from the sun by molecules in the atmosphere. And so what you can see here, though, in this is some vortices. It's a little hard to see in the visible light, but on the right we have the infrared again, and you can see in the infrared, you can see these amazing polar vortices. You see a central vortex, and then you see in the north 1, 2, 3, 4, 5, 6, 7, 8 surrounding vortices, and the south pole is 1, 2, 3, 4, 5. Different north and south. And it's been that way for over 10 years. We don't know why. And indeed, we can look at this movie that shows you is we don't get to stare at the northern hemisphere or the southern hemisphere. We just go pass over quickly. But each time we look, we see a slightly different structure with little vortices coming in, either getting swallowed up or spat out by these main 8 in the north, 5 in the south circumpolar cyclones. And so this has been a new discovery that's got us thinking about what is going on in the upper atmosphere, the atmosphere of Jupiter, and how deep are these cyclones, and so on. So this is a new revelation that has got us thinking about the dynamics. Somehow up here, away from the equator, the turbulence and the vortices seem to take over and drive these cyclones. Now, when we looked at Saturn, which indeed had many orbits looking at the atmosphere, because Saturn has only a third of the mass of Jupiter, the atmosphere is more spread out, and it has similar belts and zones, but they're just harder to see. You can just about see them, but they're sort of deeper in the atmosphere. But what we did see over the pole is that at Saturn, instead of having multiple vortices, 8 or 5 vortices, it has a hexagon. And so we have a central vortex with a hexagon around it, changing the time. So why are these so different? Maybe it's related to their different masses, maybe somehow different internal structures. We don't know. This is an exciting mystery to be solved. So Juno has been doing a lot of important science, looking at the interior, understanding the magnetic field and the clouds and stuff. But what's really interesting is we were not going to put a camera on this spacecraft initially. And then we decided, we've got to snap some pictures for NASA, for the publicity. So we put this thing called JunoCam, a camera, onto this spacecraft. And we decided to turn it into a citizen science exercise. And you can go look at this webpage where there's a lot of engagement of citizen science. Anybody can get involved, looking at the images, downloading them, playing with the images, uploading your own ones. And so what amateurs have been doing, citizen scientists have been doing, is to play around with things. And one thing they've been doing, if you look at what you could call true color, which is pretty bland on Jupiter, it's not the contrast that you see in a lot of the images that are presented to the public, because what you need to do to see the structures is to crank up the color contrast to make the red more red, the white more white. And then you begin to see the dramatic structure, a lot of turbulence, a lot of motion in the atmosphere. And these amazing citizen science have gone in and manipulated in terms of just cranking up the contrast. And you begin to see things. In fact, you see very fresh clouds, the white clouds are fresh. We call them pop-up clouds, where the, ammonia clouds are produced, uprising, condensing, and forming fresh clouds. But not only do the citizens do science, they also do art. They can play around and post their art, which is lovely. I just think this is fabulous engagement of the public in this space mission. Here's another example with lovely pop-out clouds, all sorts of new observations. And then sometimes you see something like this, like Danny the dolphin, and there's pelicans and things. People have been looking at clouds and interpreting them in terms of people and animals and trees and mysteries. I just think this is fun. Of course, the next time we flew by, it had gone. But the Great Red Spot has been there for about 300 years. And this is a beautiful picture taken by Juno, and you can see all the structures, really a beautiful picture. Now, the Voyagers, when they flew by in 1979, made movies of the Great Red Spot. It's a high-pressure storm, and very similar to Hurricane Katrina, but a lot bigger. Similar wind speeds, but as you can tell for scale, it's in fact about twice the size of the Earth. And here is a Voyager movie. The red is exaggerated, so it's in this movie, but you can see it's about twice the size of the Earth and rotates about every 6 days or so. And this has been persistent for several hundred years. Okay. Now, what size is it? Well, it's about the size, like I said, at the time of Voyager, about twice the size of the Earth. but we don't know how deep it is, somewhere between 300 kilometers and 1,000 kilometers deep. That's really just painted on the surface, even though as an atmospheric structure, it's quite large and noticeable. And indeed, the great Hubble Space Telescope has taken beautiful images, and it looks like it's getting a little smaller. So the question is, compared with Voyager, it's got a little smaller. Where is it going? Now, the true color, here is a Juno picture where there's a sort of consensus this is probably about the right color. And the question is, where does that color come from and what does it mean? Well, the idea is that ultraviolet light from the sun hits the atmosphere and causes chemical reactions. It breaks up the ammonia and the ammonium hydrosulfide, and then pieces come back together to make other molecules, maybe even liquid aerosols and colored stuff. So we see this at the Earth, and this is a picture of me on a hike here in Boulder, looking out towards Denver in the middle of winter. And there are photochemical reactions happening in the Earth's upper atmosphere. True, it's related to pollution in the case of the brown cloud over Denver, as in LA and other big cities. This is photochemical reactions that produce these aerosols in the atmosphere. So we thought, okay, you'd have ultraviolet light hitting ammonia and this hydrogen, ammonia hydrosulfide. So you would think you add UV, you would get sulfides, and sulfur's yellow, right? Well, Bob Carlson, who's a scientist at JPL, he did this experiment, and what he found was lime green. It wasn't yellow. So what is going on? So what he did was to add some more chemicals, acetylene, which is carbon and hydrogen mixed together, and gets this molecule that has some combination of hydrogen, carbon, and nitrogen, and gets the right color, more or less. So it turns out these are called alkanes, and they are the same yellow that goes in your printer to make a yellow on your inkjet printer, and it's the same yellow that makes the yellow lines on the roads. So quite a common chemical, but interestingly enough, this could be the yellow in the atmosphere. And indeed, you have this sort of crust, what we call the creme brulee model for the Great Red Spot, that you have convection bringing up acetylene from below, reacting with ammonia, you get photochemistry coming in, you make aerosols, and then, makes this layer that stays at the top, rotating around in the Great Red Spot. So how much of this would you need to color these clouds? Well, it turns out it's very little. It's just 61 parts per billion, right? So 61 molecules of this chemical for every billion molecules of the atmosphere. And what you get of the hydrogen in the atmosphere. It's a very low concentration. And the spectral index signature seems to match the observations of the Great Red Spot. So it looks like we've got the right idea, but we're not 100% exactly what the chemicals that are made. Probably some combination of hydrogen, carbon, and nitrogen. The other thing about the Great Red Spot is that it seems to have been shrinking. The time we look at it now with Juno, it's now about 1.5 times the size of the Earth. And indeed, Earth-based astronomers have been looking at the Great Red Spot over the years, and Amy Simon put together this compilation history from 1880. And if you look at this black line, it tells you the size in degrees around across the Great Red Spot. So it's gone from being about 40 degrees down to about 15 degrees. And so that's from about 2.5 times the diameter of the Earth down to less than 2 times the size of the Earth. And so it's shrinking over time. And if you extend this forward into the future, it will eventually disappear, but it'll be several decades. On the other hand, it might grow back. And, in 10, 20 years, it'll go back to being large. We don't know. This is something that we can just watch and see what's happening. So that's been a real whirlwind tour of the Jupiter and Saturn system, putting it in a bit of context of Uranus and Neptune. And I just want to thank you, answer your questions, but also mention and think about, where do you want to go next? And I would argue that Uranus and Neptune, we just had the one flyby of Uranus in 1986, of Neptune in 1989 with the Voyager 2 spacecraft. And I think it would be fabulous to go back and explore and try and understand, why is Uranus tipped on its side? How come Neptune was able to capture its moon Triton? What is the similarities and differences between this dark spot on Neptune and the great red spot of Jupiter? All sorts of exciting things, as well as their moons, to explore with future missions. And with that, I will thank you very much and stop sharing and very happily answer your questions.
Thank you very much. That was a great talk. Just have what's probably a silly question. Do the rings of Saturn also rotate? They rotate at differential speeds.
Excellent. Yes, I didn't really talk much about the rings because I sort of associate them a bit with the moons. And I thought, well, okay, I'll just deal with the planets. But the rings they're the little objects, right? Little chunks of ice, little chunks of rock, little chunks of material that are orbiting. So they're like minute moons. They're all orbiting Saturn, and indeed the other planets also, Jupiter, Uranus and Neptune, also have rings. They're much smaller and thinner and a little harder to see. But if you think about the rings of Saturn, you've got it's very thin layer. They're all very tightly confined to the equator, and they orbit. Now, what you do have is sometimes there are moons, little moonlets, small moonlets, that also orbit, and they tend to have a little bit of gravity that tend to shepherd the ring particles into a thin ring going around. So you have these multiple rings at Saturn, some of which are tightly shepherded by little moonlets on either side that push them into this narrow ring that goes all the way around. Lots of very exciting dynamics. Yeah.
Do the rings rotate at the same speed as the surface of the planet?
No, they orbit. Okay, so they go around at different speeds depending on how far out you are. Okay, so you'll go faster if you're closer, slower if you're further out. Now, there is at some point you get to what we call synchronous orbit. Now, for the Earth, that synchronous orbit is out at 6.5 Earth radii. And that's where we put satellites, where we want to stare down at Earth and map the Earth or communicate with one place over the Earth. So we have geostationary satellites up in the sky above us that are orbiting with the United States around as the United States spins on the Earth, goes around every day, every 24 hours. That satellite overhead also goes around the Earth in 24 hours and is able to communicate constantly with the United States. Okay, similarly for other places. Now, for Jupiter, that distance is 2.5 Jupiter radii. So the rings of Saturn, the rings of Jupiter, are all inside that distance, and so they're actually going around faster than the spin rate of the planet. Okay, so it's not synchronized with the spin rate of the planet.
We called Jupiter a gas giant, but it looked like most of the mass of the planet and most of the volume of the planet was metallic hydrogen. Is that correct? And it is that core that's spinning with a huge, I guess, magnetic field that protects it from the sun's radiation and keeps the hydrogen from blowing away? Close even?
Sure. So indeed, at some point you go into the planet. It's a gas at the top with clouds and so on and so forth, condensed aerosols and stuff. But as you go deeper, at some point, the hydrogen turns into a fluid, right? So we call it a gas giant, but indeed, you get deeper inside, it's a fluid. We don't know whether or not there really is a solid layer. But part of the problem is the pressures are so high and the temperatures are so high, we don't understand how liquids behave, those pressures and temperatures. We can't ask NSF to give us funding to take 1,000 elephants and stack them up and on top of hydrogen to measure those pressures. And there's no other way of measuring pressures that high or making hydrogen that pressure and temperature in the lab. So we don't really know how hydrogen behaves. We have to use quantum mechanics to describe the equation of state for hydrogen at those pressures and temperatures. But it pretty much, we're confident that it is a liquid that is convecting and moving around and generating the magnetic field deep inside. So yes, maybe strictly speaking, we should call them fluids, or we should call them non-solids. I don't know what. I mean, gas giants is just easy. But I agree that it's a little bit of a misnomer.
I have a question about these magnetic fields that you described to us. On Earth, we hear that, periodically the poles flip. And I look at what you have there, and you've got so much turmoil and chaos going on there. So tell us a little bit more, because I don't understand at all what's going on those. Tell us about magnetic fields.
So for the Earth, we have a magnetic field that's generated in the iron outer liquid layer of the Earth's core. So the innermost core is solid, the next iron, the next layer out is liquid iron, and then there's rock above that. Now, that iron inside, liquid iron, turns over and generates a magnetic field inside the Earth. And that magnetic field, what's interesting is, because we have volcanoes on the Earth, every time a volcano spews out lava, there's a little bit of the ambient magnetic field at that time frozen into the lava when it solidifies. So if we go and look at a place where there's been periodic lava spewing out, we can measure the magnetic field at that time when it was spewing out. So say we look at the place where the center of the Atlantic drifts apart, and there's a volcanic material spewing out at the center of the Atlantic along that center point. You can then see the magnetic field on either side flips up and down as you move further out, because the Earth's magnetic field has flipped. And we can date that when it did a flip by looking at the age of the rock using isotope dating of rocks. And then we can say the Earth's field was pointed up, pointed down. Okay. Now, for the Earth, that's random. It's not a systematic period where it turns over. It's on the order of 100,000 years. It's quite long before it flips. Okay. Now, for the sun, in complete contrast, we have a dynamo deep inside, and that's, again, it's actually a plasma, electrons and ion and protons that are moving around inside, generates a dynamo. But for the sun, it's been a fairly regular for the past few centuries. Every 11 years, it flips. Up, down, okay? And it's regular. So here's a dynamo on a big thing, a star that is regular. Now, Jupiter is in between. It's about the 10th the size of the sun and about 10 times the size of the Earth. And it has a dynamo and the magnetic field. We've measured the magnetic field since about 1957 or maybe 56, can't remember. But radio emission have told us that Jupiter has a magnetic field. And it's not flipped. It has, we think with the Juno data, we can see it maybe drifting a little bit, the way the Earth's field drifts a little bit, but it's not flipped. But that's only been 50 years, right? 60 years. It's not a whole lot of time. And so we don't know whether or not the dynamos on Jupiter or Saturn flip or not. And as for Uranus and Neptune, they're highly irregular, so they probably do, but we've got one measurement of Uranus and one measurement of Neptune. That's it. That's it. Once, one time, one place. And it was irregular. So we don't know about Uranus and Neptune. So it's really interesting that these very different planets have very different dynamos with very different behavior. Big topic.
Relative to our own lived human experience, these things take a long time. And we think that if we live to 100 years old, it's a long time, but it's really just a microsecond.
Right. Yeah. You feel that when you go to a big geological structure like, the Grand Canyon, or, you see a big volcano or something, you're like, that's big.
So you spoke about our sun as having one element of our sun having a period of every 11 years. And you said it continues like that.
Yep.
And so if it continues like that, it should be able to be measured. In other words, we should be able to determine why that is. What's causing that?
Well, there are different things. Measuring it and explaining it are not necessarily the same. It helps to measure it,
Yes.
to be able to.
What I mean is that something is causing that and controlling it.
Yeah. Yes. And so dynamo theorists are working on that, trying to understand it, indeed. So, we have, you've probably witnessed aurora recently, because we're even in Florida, there's been aurora in this past few months, because we're at solar maximum right now. The sun is at maximum activity. And then it sort of dies down, and then the field flips and it grows up in the other direction, and then it goes down and then flips in the other direction. So this 11-year cycle of flipping is related to the solar maximum, the cycle of maximum activity, and the effect it has on the Earth, driving the Earth's space weather. So it would be. We've got a pretty good measure of that. We've been measuring that since the 1800s. In fact, sunspots go back for thousands of years. Chinese people were observing it, thousands of years ago. But just knowing that we go through solar maximum every 11 years does not really help us explain. It's a nonlinear feedback system trying to understand fluid dynamics of a material you don't really know, we don't really understand, and then quantifying it in a way where small scales can build up to affect larger scales and so on. It takes a lot of computational work, and then you get a result, and how do you understand it? So it's difficult. People are working on this, but dynamo theory it's come a way in the past few decades, but it's got a ways to go. Maybe with big computers, it'll move forward. Yeah.
I've got two questions about Saturn. You mentioned that for Jupiter's poles, we've got 8 vortices on one pole and 5 on the other, but for Saturn, we have a hexagon on one pole. Is it a hexagon on the other pole too? That's my first question. And the second one is regarding the rings. Some of these rings are really quite broad, not thick, but broad. Does the outer edge of the ring rotate at the same rate as the inner edge of those broad rings, or they rotate at different rings? And so there is a churning type of effect that goes on within the broad rings. Is that correct?
That is correct. So it looks broad, but it's not a solid piece, right? It's still made up of little pieces, okay, that are moving separately, okay? They may bump into each other, yes, so there's some friction there, but mostly, the inner edge is moving faster than the outer edge, okay? So there's differential rotation because of the orbits they're not coupled to each other. Now, with the other question was, though, is there a hexagon on both hemispheres? And I'm embarrassed, but I don't know. I should know that answer to that question. I'm not going to pretend I do know when I don't. Someone can Google it and put the answer in the chat. I'm sorry. I should know that, and I don't.
Don't believe what you read on Google.
There is a question here, which is Jupiter's second star in our solar system just not big enough to ignite? And the answer is yes. It would have to be 10 times bigger. So I say Jupiter is a failed star, but a very successful planet. But the pressures are not high enough to ignite and get hydrogen to cause fusion and release nuclear energy, which drives the sun, makes it so hot. Yeah.
Can you read the other online question, the other chat?
How does one know that the method of measuring interior Jupiter density is valid? Is it just theoretical? I'm just fascinated by how you figure out what these crazy pictures data mean. Yes, indeed. Like I said, we don't really know how hydrogen or helium behave under these high pressures and high temperatures. So what people do is they say, okay, I'm going to use my quantum mechanics magic to say how hydrogen behaves at high pressures, high temperatures. So I vary the temperature and the pressure. What is the density using the quantum mechanics? And then take that model and add up the density, the mass, make a model of Jupiter with the density decreasing with distance and the pressure decreasing with distance and temperature and so on. And then you say, add that all up. Does it match the gravity data that we measure with Juno as we go over? You say, no, it's not quite right. So what if I tweak that a little bit? What do I have to do to change the distribution of mass in order to match the observations? And so we've got a set of observations which are pretty good measure of the distribution of mass inside Jupiter, but it'll be a while before we sort out the equation of state. The theory has to sort of catch up with the observations, to be honest with you. We've got a ways to go there. There are multiple interpretations. I just showed you one, that it was fuzzy up to this distance. And there's a fairly strong agreement that it's not the strict layers that the textbooks show, that it's much fuzzier inside. but the details are not quite there because we don't have the theoretical understanding of how hydrogen works at these high pressures and temperatures.
In any case, I think we can conclude that Jupiter is a very violent place.
Definitely.
Elon Musk notwithstanding, I think that humans are not going to go there. I have one question, and you were referring to Uranus and Neptune, and that they also are constructed of this ionized mass of water.
Yeah, it's not hydrogen, that metallic hydrogen, because the pressure isn't high enough.
Yes.
It's water and ammonia and various ions mixed in with the water to make it conducting, in the same way that our ocean is electrically conducting, because you've got salts, sodium chloride, and other things like that dissolved in the water, which makes it electrically conducting. And we think that inside Uranus and Neptune, there's a water layer that could be electrically conducting, quite weak conductivity. So it's not a very strong dynamo that makes a weak shell dynamo in these planets. But it's very poorly understood or constrained, and that's another reason why we need to go back to Uranus and Neptune.
But aren't they frozen?
No, it's not. It's probably got warm enough deeper down. So what the reason why the planets are hot, and particularly the big ones are hot, is that when you think about material coming together, the gravity pulling material in, that material comes in and it bashes in and collects and accumulates to make the planet. So as the planet is made, it brings in material and bashes in, and you end up heating the planet inside, and the denser material sinks down. That also releases heat. So you have a hot interior of a planet when it's formed, and there's good evidence to believe that the planets are all pretty hot deep inside when they were formed. But then you think about it, a big planet and a small planet is like a big potato and a small potato. And you know that a big potato stays hot for a long time, whereas a small potato or the peas on your plate cool off very quickly. And so the smaller planets and moons and so on all cooled off quite quickly. But the big planets like Jupiter, Saturn in particular, remain very hot deep inside. And Uranus and Neptune remain fairly hot deep inside. Okay? So you have to think about the history of how they got to be the way they are.
But
now,
on the surface, wouldn't they be frozen?
not solid. They are gaseous. They're gas. They're gas on the outside. So some hydrogen helium for the outer layer, with mixed in ammonia and lots of methane. Methane is what absorbs the red light to make it look blue. Make Uranus and Neptune look blue. They look blue not because it's the same way our atmosphere, but because they have methane in the atmosphere, which absorbs the red light coming in. So it doesn't, what gets reflected out is only blue light. Does that make sense?
I've been misinformed because they call them the ice planets.
Yes. Oh, that drives me nuts. It drives me nuts. Okay. You just confirm what I've been saying to my colleagues. You mustn't call them ice giants because people will think that you can skate on the surface. No, you can't. These are gas giants. They call them ice because planetary scientists like to call water, ammonia, methane ices, even if they're gases.
I just looked up the poles on Saturn. Yes. It's hexagonal in the north and a circular disk in the south.
Interesting.
NASA.gov, so it's not AI.
Okay, interesting. Thank you very much. Great.
That's Mary Crispin, and she is a scientist herself,
Right.
but not a physicist, I don't think.
Great.
Yes. Well, any further comments, questions? Well, thank you all very much, and thank you, Professor Bagenal. It's been wonderful.
It's a pleasure. Have a great day, everyone.